Hmm? Has he gone live? Gone live? Good evening to everybody, and welcome to this special webinar as part of the celebration of the Azadi Ka Amrit Mahotsav. It's very nice of a large number of our colleagues to join today's program, in which we have a very eminent speaker. As you are aware, as part of this eminent lecture series, we have been trying to highlight the achievements of the science and technology, and particularly in the Department of Atomic Energy since independence, through lectures by stalwarts in different domains. And it's a great pleasure for us to welcome amidst us today Shri Surendra Sharma. I will just take a few minutes to introduce him, even though he may not require introduction to most of the audience. But our students and our young faculty who have joined from different places, for their sake, I would like to say a few words about him. Sri Surendra Sharma is a graduate from IIT Kharagpur and from the second batch of the DRC training school. He is one of the pioneers of the development of heavy water technology in India. In fact, the story of the heavy water program, the development of the indigenous capability in the country, is one of the great success stories of our department. And it is he's the art person to explain to us his perspectives on how it all evolved. Sri Sharma joined heavy water and stable isotope production section of BRC in 1959. And he was instrumental in the development and deployment of heavy water technology in India with indigenous efforts. He played a pivotal role in setting up the hydrogen sulfide water-based heavy water plant from concept to commissioning, including engineering design based on VLE data generated from pilot plants set up and operated at the heavy water and stable isotope production section BRC. India's first heavy water plant based on this above technology was set up at Kota with great contribution from Shri Sharma ji. His expertise was further utilized in setting up double capacity plant at Managuru, which went on stream in record minimum gestation period and achieved the rated capacity in the lowest period among the world's contemporary similar plants. Shri Sharma contributed significantly in commissioning and stabilized commercial operation of these plants and further optimizing the process parameters for lowest resource consumption and maximum productivity. Shri Sharma took over as the chairman and chief executive of Heavy Water Board in April 1992 and steered the entire gamut of activities in the domain of heavy water until September 1995. In that capacity, he actively contributed to large-scale production of heavy water for countries' nuclear power program using multiple technologies at plants located across the country. And he also initiated diversification activities of the Heavy Water Board. Shri Sharma contributed to creating India's global imprint in heavy water, making the country the largest producer of this crucial material and the world's only country using multiple technologies. Under his leadership, India bagged an export order from South Korea for supply of 100 metric ton of heavy water against stiff international competition. After superannuating from DAE, Shri Sharma has been professionally active, providing expert opinion and guidance on relevant technical issues, besides leading a consultancy company. Shri Sharma has co-authored the book titled A Dream Comes True, covering the India's heavy water program. He also co-authored the book The Man and His Vision, a tribute to Dr. Vikram Sarabhai on his century celebration. You will all agree with me that we are in for a treat, listening, I should say in a very crude language, from the horse's mouth about how the heavy water program became a success from a fledgling program to a world leadership. So it is a great pleasure for us to welcome Shri Sharma Masters. I request him to deliver his lecture. Just sit here. This mic is here. You can sit, he will charge it. Ready. Yes, that's fine.
Namaskar. Thank you very much, Professor Rao, for introducing me and saying some kind words, some of which I really do not deserve. And thank you very much for giving me an opportunity to relate the saga of heavy water production in India, a story which meant that from heavy water became from scarcity to surplus, and a story of which I have been a part of and I have lived through it. Now, basically, heavy water is a deuterium oxide, as all of us know. I mean, but I have to introduce heavy water. It's a stable isotope of hydrogen, and it's the only source of deuterium is actually hydrogen of water in nature, where the occurrence is something like 140 to 150 ppm. It's an excellent moderator for certain type of reactors. Moderating ratio is, of course, virtually the power of the moderator to slow down the neutron so that it come within in a nuclear reaction, so that it come within you can help propagate the reaction. It's actually ratio of the neutron scattering cross section to neutron absorption cross section. Now, the heavy water is actually one of the best moderators. Its the moderating ratio is something like 21,000 as compared to 58 for water and 200 for graphite. There are other moderators also, beryllium, etc., but nothing comes close to heavy water. Now, heavy water is a key input for supporting the PHWR program of, the stay of PHWR program, as you know, is a stay of Indigenous Nuclear Power Program, where it serves as not only as a moderator, but it also serves as a coolant. Just to give you an idea about the magnitude of the whole requirement of heavy water, about a 220 metric ton of PHWR requires about 220 metric ton of heavy water. But subsequently, there have been some improvements in the design, our own design of PHWRs, and there you need only 485 metric ton for a 540 megawatt unit. And for the present avatar, that is the 700 megawatt unit, you need 525. Then smaller quantities are also required for makeups and non-nuclear applications. Well, self-reliance was a key factor for the success of the program, and indigenization and bulk production of the heavy water was the need. Then subsequently, actually, this was just to give you an idea about the magnitude of the production that you need. Heavy water actually was first prepared in a laboratory by Gilbert Lewis, an American scientist in 1934, soon after discovery of deuterium by Urey, another American scientist. Heavy water actually has a checkered history, but we won't get into that because initially it was really associated with the weaponry program. It's only later on that it got importance to get into the power production realm. As far as India is concerned, we take a leap in time. On the dawn of its independence in April 1948, Dr. Homi Bhabha made a visionary statement. I quote, "Government should explore immediately the possibility of utilizing cheap hydroelectric power in India for manufacturing heavy water on one hand, for our own requirement in pile, and also on the other hand for sale to other countries," unquote. But it was not only a vision, but could also be termed a dream at that stage. The this whole thing is a story uh, of fulfillment of his dream, really, because eventually we not only produced heavy water uh, and became Atmanirbhar, which was the mantra of generally DAE has a penchant for that, but also became exporters of heavy water. Now, there are very many methods for separating deuterium, but most of them are confined to that. For instance, there's a gas diffusion, there's so many methods are there. But for large-scale separation of deuterium, generally, the technologies that are employed, I've listed it out to them. Some of them are very good, but they have merits and demerits, all of them. And you have to choose the right technology depending upon where you want to set up the plant. Then the first and foremost and the technology which we also have employed is electrolysis of water, in the sense that when you electrolyze hydrogen and deuterium and hydrogen, gradually the water becomes enriched in deuterium. This has a very good separation factor, and the advantage is that you can have an unlimited feed throughput because water is the source, but it has a very high specific energy consumption, and you need very large electric power. I'll talk about it a little later, but it has been employed in India for production of hydrogen by fertilizer plant at Nangal, and then that hydrogen has been used by us for producing heavy water. That technology we'll talk a little later. Then we have the distillation of water. Again, water is the source, so you can have a unlimited throughput. The equipment is simple and operations too are simple, but it has a very low separation factor and therefore very high specific energy consumption. Then distillation of hydrogen, it has a very good separation factor, and the specific energy consumption is also low, but the demerit is that it has a high refrigeration cost. The plant also gets quite complicated because of cryogenics involved, and consequently also because hydrogen, you won't make it into a standalone plant. You'll take the hydrogen from fertilizer plant or somewhere. So your capacity gets limited. Then we have isotopic exchange processes. The foremost amongst them is H2S H2O isotopic process, which has a good separation factor, and the feed could be anything. So you can have a plant capacity of any level that you want because the water is the source. The kinetics are fast. It has a moderate to high specific energy consumption. But the biggest disadvantage and challenge in this technology is that it employs H2S, hydrogen sulfide, which has a very high toxicity, and the system is also very corrosive. Incidentally, this is the method we have employed for developing our own indigenous technology. Then we have a similar isotopic exchange method, which employs hydrogen, that is exchange between hydrogen and ammonia. It has a good separation factor. The specific energy consumption is moderate, but initially the first few plants needed a high pressure operation, and that posed quite a lot of problem. Pressures were of the order of 600 kg per square inches because it was hooked on to the fertilizer plants. And it requires catalyst, which has its own problems. And the big limitation is that it is parasitic to fertilizer plant. It depends, the capacity gets fixed by the amount of hydrogen that you can get from the synthesis gas from there. And also performance depends on the quality and quantity of, as well as the performance of the fertilizer plant itself. Then we have exchange between hydrogen and water. This has a very large separation factor, its specific energy consumption is low. You can have a unlimited feed throughput, but the commercial problems have commercial production has not been possible because there are very severe problems about the catalyst which is required. So it has not been much in favor. I just want to show you the technologies that we have employed. Our, our first and the first plant that we had was at Nangal, which was based on distillation of hydrogen. The very cheap electric power was available at Nangal, and so a fertilizer plant was set up there. And they were producing hydrogen for their synthesis gas by this electrolysis of water, and the hydrogen was being tapped for our plant and liquefied and distilled to get deuterium. Then the other technologies that we have used, which again I'm repeating it, the indigenous one, fully developed by us, is the exchange between hydrogen and H2S. Now this is basically, I mean, not going into too many details. Basically, the deuterium gets transferred into the liquid phase. And so at one low temperature, the liquid gets, deuterium gets transferred into liquid phase, and at a high temperature, it gets reversed. In other words, what we do is H2S is employed, like it circulates through the plant, picks up deuterium from the hot tar, and gives it up in the cold tar, where the liquid gets enriched and you draw the product. Then we have a similar process, but employing ammonia and hydrogen. In this, we have two versions. One is a monothermal, where again the principle is the same. Ammonia is used for circulation and picks up deuterium. I mean, again, it gets transferred, the deuterium gets transferred to the liquid phase at a certain temperature. And another version of the same exchange process, like we have for the H2S H2O, which is a bithermal one, where the similar concept is used. Here also the ammonia is used, circulated, picks up the deuterium at a certain temperature and gives out at another temperature. Now, we face certain problems because this ammonia hydrogen exchange process necessarily has to be hooked on to a fertilizer plant for its feed from the of hydrogen from the fertilizer plant. We face some problems in this along the line, and we have had to suspend production in some of the plants because the fertilizer plant changed its technology altogether, and the feed from there was no longer compatible. So we worked on another technology, again indigenous, where we have tried, we have developed the technology, but we have not employed it for major production because it also entails further modification in the rest of the plant. But basically, this technology is to make it independent of the fertilizer plant or the ammonia hydrogen exchange process-based plants. And we demonstrated it's working, but we have not used it further. But it's a viable plant, and it can make those plants free, I mean, independent of the fertilizer plants. Then actually, going back into the history a bit, in 1951, I've already mentioned that 48, Dr. Bhava dreamed of, he had a vision of producing heavy water, not for only our use, but also for export. So in 1954, Dr. Bhava mooted establishment of a heavy water plant at Nangal, the first technology that I have mentioned, in conjunction with a fertilizer plant. Fertilizer plant was based on production of hydrogen by electrolysis, as very low cost power was available. So a 14 ton per year heavy water plant was set up based on, this was a German cryogenic distillation of hydrogen technology. Hydrogen was being tapped from the fertilizer plant and liquefied and then distilled. Well, this plant produced the first drop of heavy water in India on August 9, 1962. It's a red letter day in the history of India's heavy water program. Well, it was a partial fulfillment of Dr. Bhabha's dream that we produce. The plant operated with diminishing capacities due to fertilizer plant constraints until 2002, where it was finally uh, given up. I mean, dismantled because it had done its life. Now, the production from Nangal plant was much too meager to support the research reactors and India's nuclear power program, indigenous power program, I would say, essentially based on PHWRs. Therefore, an intense drive was undertaken for augmenting the production in the 1960s. A separate entity, Heavy Water Projects, was constituted in 1969 for this purpose. And incidentally, when the emphasis shifted from the setting up of the projects to operating them, we had enough plans and the emphasis shifted. So this unit was rechristened as Heavy Water Board because the emphasis has shifted. That was 20 years later, that is in 1989. When we, around 1968, crucial decision had to be taken. You see, because what was happening, the nuclear power program was catching up. The heavy water program emphasis had come in a little later. So we were somewhat lagging behind the whatever was the requirement. It was evident that if we don't hurry up, we may become a bottleneck. So crucial decision had to be taken as to the path for producing large quantities of heavy water to meet the growing demand for nuclear power program. On one hand, we had the indigenously developed H2S exchange-based technology, though proved only on a small pilot plant. And on the other hand, a ammonia hydrogen exchange-based foreign technology proven on a plant scale, though that only for a short while. Well, it was decided to employ a two-pronged strategy. That is, put faith in our own technology. That was great because we did put faith in our own technology and build a plant based on it. At the same time, making use of imported technology for building other plants to ensure that we catch up with the projected requirement of for the PHWR program. So the steps were taken to set up a 100-ton per year plant based on our own technology at Kota, and two plants of 67-ton per year at Baroda and 71-ton per year capacity at Tuticorin. These two were to be based on imported technology and had to be hooked on to fertilizer plants. It was done in quick succession between 69 and 71. Then another plant of 62 tons per year capacity was sanctioned in 1972 for being set up at Talcher. Based on the projected requirement of heavy water in 1982, but we had already started producing, but yet it was reviewed and it was found that we got to add further, we had to augment the capacity further. So based on the projected requirement, in 1982, sanctions was accorded for setting up a 185 ton per year H2S H2 exchange based plant at Manguru. That was virtually a scale up of Kota plant. That is almost double the capacity of Kota plant. Again, our own technology. And also a 110 ton per year ammonia hydrogen exchange process at Tada. These were virtually the second generation plant because we were working on Kota and Baroda and all that. So we had already learned quite a bit and we were able to make improvements and all that. Well, 4 years later, another plant of 80 ton per year capacity based on ammonia hydrogen exchange process was sanctioned for being set up at Hazira. Now, I have taken the liberty of dwelling a little bit on our indigenous technology because It's not that we did not work very hard on making the imported technology work, but as far as the indigenous technology was concerned, we faced a lot of challenges and all that. I want to mention those. The point was that we have developed this thing on our own from scratch, as Professor Rao had mentioned in the introductory remarks, that we actually uh, did a work on these, and we have done the work from concept to commissioning. It's not that we have got the technology from somewhere or something, and we worked on the concept and we did all the intermediate work of design and everything on our own. So, well, it was to be, I might mention that this process was known as a process being used elsewhere for production of large quantities of heavy water. Basically, it was in US, and but that was connected with their weapons program. They were producing heavy water for using it in the reactors for producing plutonium. So the technology was highly guarded, and not much information was available. So we had to develop it on our own right from scratch. I mentioned that the technology was developed in Hall to Embark, but it was done on a pilot plant. We had set up a pilot plant. We also put some test loops, etc., studied the uh, materials, measured all kinds of parameters, surface tension, and, got some information, we got some enrichment done. All that was done, but the pilot plant size was too small. And what we were looking at was a large scale plant for production of heavy water. So it was too large a scale up. In the chemical engineering, you don't use this kind of a scale up. But we had no option. We had uh, proven the process. We had got some data, and we felt confident that we can do it. But still, the scale up was quite a bit, and that did pose certain problems. Then, of course, the equation looks so simple, but the process and engineering for this technology has been very complex. It's a different ball game altogether as compared to other chemical plants. And I'm talking of a time when there were no softwares available. I think the present generation, uh, my friends may not be able to appreciate it. Well, it was a time that you still had to take your textbooks and design from from RAM, that is ab initio itself. And there was very little computer support available. Matter of fact, we had graduated out of the slide rule era, but still, at the time that we were doing the initial work, the very little computer support was available. I remember one of our colleagues will collect all the information what needed to be processed. He'll write the programs, punch the cards, and we would get some small time at TIFR for the computer. And so there was very little, and there were no software. You couldn't just. So this was also a big challenge. We were all fresh. Most of the team was fresh with very little experience, and but we did it. Another challenge that was faced was, as I mentioned, the occurrence or the abundance of deuterium or heavy water in normal water is very low, 100 parts per million, say. And then we have to upgrade it, we have to enrich it to 98.4%, which is the reactor grade. So very large volumes needed to be handled, which means that you must have very large uh, size of vessels and very large plant itself. But then you could not do it because there was a restriction on size of vessels. You cannot. Actually, we did think of setting up the facilities at fabricating of the equipment at site, but then the quality would not have been as good. So it was decided that we'll have fabrication done only in these shops and bring them in pieces and assemble them aside, do the treatment, whatever was necessary. But even to bring them in pieces, there was a restriction on the size. So that also put a restriction on size of the vessel that you could use and optimization of the cascades and all that. Then the biggest challenge was and which was the primary consideration, was the safety. This service is a highly toxic service. I mean, this is where we have H2S, and H2S we hold in a 100-ton plant, something like 200 tons. And in a Malguru type of plant, some 400 tons of. And H2S, I'd like to just draw your attention to the toxicity of H2S. You see, actually, these are the standards that we use when we design the plant. Now, of course, the standards have been tightened further. But like you could tolerate, I mean, you could tolerate it, concentration of 10 ppm for 8 hours in the plant. But you know, when you get into the concentration of something 700 ppm or something, then well, that's diesel. So one had to be very careful. As a matter of fact, the H2S, you also, you know, if you go to a place, you smell H2S, but that's only in lower concentration. Once it gets to a certain higher concentration, you don't even smell it because it affects your olfactory tissues, and so you are blind. So this was a very big consideration, and all our design had to keep this thing in mind. Then also it has a certain explosive limit. And incidentally, this slide also shows the toxicity, I mean the hazards of ammonia, which is for other technology, but I won't have time to come back to it again. But basically for this thing, it became a very prime consideration. Actually, uh, because of this, uh, we had a lack of infra. Yeah, the toxic service is one thing that the prime consideration. As a matter of fact, our philosophy even today, when we are operating the plant, our instructions are you have to take care of safety first, whether you produce or not, that's secondary now. So that was the kind of philosophy we used right from the beginning. Now, it was a time when there was a complete lack of infrastructure and experience on part of fabricators and equipment suppliers. Like, you know, the very few fabricators who could handle and fabricate clad materials. Like in our service, we need carbon steel clad with stainless steel. And at that time, there was not enough experience for this thing. Then also, the suppliers of equipment for this specialized kind of service were not there. They were still under development. You see, like gas booster, I have mentioned. I said in the process, you have to circulate H2S gas. And this is very large volume. The capacity of the gas booster is something like, the rating would be something like 2 megawatt. Then you need special pumps with special seals. And you need walls with special materials and special seals because you cannot allow any leakage of H2S, and also the service is very corrosive. So we had to do a lot of vendor development, but we needed to import quite a bit of equipment and materials also because of the, well, it was a different story for our subsequent plans, but that was an era where we and as I mentioned, the not only the vendor development, but we also were in an era of a scarcity. I think some of the old timers would remember that even the basics, such as cement and steel, even those were very scarce. You needed a permit. You needed to have some kind of a allotment And this is, of course, on the project side. And then, of course, there was a very big shortage of foreign exchange. We needed to import something, but foreign exchange was very scarce. Sometimes it was tied to a specific country aid. So you may like to get some equipment from some country which may be most suited, but then eventually you have to import it from some other country because the foreign exchange is tied up to that country. Now, a complete embargo got imposed on aid and exports to India as a sequel to our peaceful nuclear experiment conducted in 1974. It was a big blow to Kota Heavy Water project schedule because we were in the midst of a Kota project, but it turned out to be a blessing in the long run because the program for shifted. The more emphasis came for bringing, for going in for more indigenization and a more intensive vendor development. Well, this, as I said, it was a blessing in disguise because uh, the setting up of the next plant became very much easier. Then in the plant, we had to uh, build in a lot of safety related, as I said, safety was a prime consideration. So the features that are built in this H2S H2 exchange plants is number one, we have to have very special seals for rotating equipment and valves. We got to provide closed vent and drain system because we cannot afford to have H2S leaking. Then carrying such a big inventory of H2S, it was imperative that in case of an emergency, you need to dump the H2S in a hurry. So you have to have a flare system. An affluent system had to be very elaborate because the limit set for affluent was something on the order of pp parts per billion. That means you cannot have something like 20 or 40 ppb H2S in the affluent. Then the H2S areas, I mean, since this H2S, we had to have a very good continuous monitoring system for H2S, not only around the units which were handling H2S, but also around the plant with signals and alarms coming to the control room. And in the areas that you have H2S, you needed to go only with the breathing air gear with you and also have a buddy with you. That means that buddy has to accompany you, but has to keep a certain distance because it should not, in case of a mishap, you being overcome with H2S, there's somebody to rescue you. So these were some of the very special. But in addition, we also provided a building with having an air supply of its own, a stored one, which could give you breathing for in the number of people that it's supposed to house. That means in case of an emergency, you move to that building. There'll be a manifold which will be fed by uh, clean stored air. You plug it in and stay there, keep breathing till the emergency gets cleared. So these are some of the features that required to be built in. And of course, you have exclusion zone and emergency preparedness plans, which is of course common with the other nuclear plants. But the S2S entailed quite a big uh, burden on the design and a lot of features had to be built in. Now, another very special feature for this process is that it is very long equilibrium time. You see this building up the concentration from 150 ppm say to around 15%, which we do in the exchange unit, and further, of course, we are doing it in distillation unit. The bulk of the work for separation is done in the exchange unit. To build up the concentration to 15%, you need uninterrupted operations for 24 days. If you have an interruption between a trip, well, you're back to square one, and then you produce nothing. Of course, subsequently, we have devised ways and means that we salvage the situation. But the important point is that all your equipment, all your procedures, all this thing have to be very reliable, because so that you don't have any interruption. And of course, there are other fine points you have to control, L by G ratios, etc. And another headache in the operation is that all said and done, you provide certain ways and means that your corrosion is minimized. But if you don't have a very good control on your water quality, the sulfur may get precipitated. There will also be some corrosion products. They get carried over to certain parts of the plant and choke the lines and create problem. So not only you have to take care in the operations, but you also have to have a very proactive maintenance. You have to have annual turnaround. Every 4 years, you have to sort of take all the hydrogen and everything out of the plant and do a very thorough inspection and make sure that you have not eaten up your corrosion allowance. Then the quota plant was integrated with RAFs, so that also brings in some complications, because you've got to get an uninterrupted supply from them. Then you also have to do take care of the condensate and return back the condensate to them. Of course, this problem was overcome with our original concept of having a standalone plant. So the Manguru plant, we provided a captive power plant. Uh, all these were, it was really a formidable task to overcome all these odds, but we did it. We mastered the technology, and the two plants at Kota and Manguru, based on this technology, are performing very well, producing beyond their rated capacity, which amounts to the major share of the total production. So that's for our indigenous technology. Now, I just want to mention how we happen to get to quota and got integrated with RAPP. You see, way back in 1960s, preliminary work had been carried out on conceptualizing 200 ton per year capacity plant based on H2S S2 exchange process, our own process. It was to have two streams of 100 ton per year each and a captive power plant based on coal and steam cycle integrated with heavy oil production unit. You see, coal was the cheapest source of energy at that stage. So we were looking for sites to locate it on the pit heads of the coal mines. Later, it came to light that RAPS 1 and 2 at Kota were capable of generating about 10 to 15% of extra steam over the rated capacity. Thus, steam, the main source of energy for the process, could be available at a very low cost. However, that was low cost means an incremental cost. It was almost like 2.5 rupees per million BTU, which is really a very low cost of energy. However, the quantity available was adequate to support of only 100 ton per year plant. In view of large economic advantage and ready availability, land and some infrastructure, as compared to setting up a greenfield project, it was decided to set up a 100 ton per year plant in the vicinity of RAPS, integrating it with it for steam and power supply. This was a smart move, but reduction in production capacity threw up need to add more capacity based on another technology. Well, anyway, Kota project was sanctioned in 1971, and we went ahead with a 100 ton plant. Subsequently, by 1981, confidence had developed in the indigenous technology to the extent that even though Kota plant was still under commissioning, a plant having double capacity of Kota plant with its own integrated coal-based power plant, the original concept, was sanctioned to be set up at Manguru. This proved to be a wise decision, because even though Kota was not completed but worked out well, and based on Kota experience, Manguru plant could be brought up for full production level so much quicker, much better than what has been done in other plants in other countries. Now, as far as imported technology is concerned, that is the ammonia hydrogen based exchange based technology. I just want to give you a slight historical perspective. The French Atomic Energy Commission had developed in collaboration with a coal company this process. They set up a 20-ton per year heavy water production plant in conjunction with a fertilizer plant in 1968. Well, it worked only for a few years because it was hooked onto a fertilizer plant and there was an explosion there. It took very long time to rehabilitate it, but they didn't restart the high water plant because I think they did not need heavy water anymore. So as a French to Indo-French collaboration, this technology was offered to India through a consortium named JALPRA, which comprised of French companies having experience in process, engineering and construction. In 1969, HWP, will excuse me for using HWP somewhere and HWB elsewhere because they were both synonyms. HWB signed a contract with JALPRA for a turnkey supply of a 67 ton per year capacity heavy water plant to be set up at Baroda in conjunction with Gujarat State Fertilizer Company, which was employing a high pressure technology, about 600 kg per centimeter square. So it was a turnkey project and all the equipment was to come from there. But we persuaded them to procure low pressure equipment locally. 2 years later, as I mentioned that quota, our own technology plant had been pruned down to 100 tons, so they will need to augment the capacity. So another 2 years later, in 1971, similar contract was signed with JALPRA for another plant, that is at Tuticorin, with a capacity of 71 tons per year, in conjunction with SPIC fertilizer plant employing lower pressure. So this became a little better, much easier plant. Here we had a more of indigenous component and more of our Indian participation. Well, with the technology made to work, I'm again doing a little jump in time, but with the technology made to work after debugging, making lots of improvement, it was a big struggle and assimilating it. I taken the liberty of saying that we virtually indigenized it. So on similar plants of 110 ton per year and 80 ton per year capacities were subsequently set up at Thal and Alvira respectively on our own. Here we virtually done it on our own. Now, something I want to mention about the Baroda plant. This process of ammonia, hydrogen exchange, it became possible because of a breakthrough, and that was because some very specialized, and I would not only say specializing, but an amazing type of trays, which are known as ejector trays, that were developed. This led to the process being adopted for industrial plant built at Mazagan, France in 1968. These ejector trays employed canned motor rotor pumps inside the exchange towers. See, we had to have penetrations in this high pressure equipment. The electrical cables had to be passed through for running the pumps. Each stage was about 2 meters high, and the liquid had to be pumped inside. So this is also needed special glass seals for cable entries, which again are very fascinating engineering feat. Then Baroda plant faced large number of major problems during commissioning and operations, some process but mostly kept related. Even though it was a similar plant which was set up in France, but perhaps Baroda plant needed much higher pressure. It was operating at much higher pressure, and also the equipment that the vendor Jalpa chose perhaps had it lacked certain integrity or whatever it is. It took very long time and it was a very big struggle to make the Baroda plant work. Actually, a failure of one of the components even led to an explosion. and led to a long delay in commissioning and bringing the plant into smooth operation stage. Though, actually, I do not know if Dr. Kakotkar is listening to it, he would remember that he and one of my colleagues, Hiremat, they worked on the analysis of failure for this component, and it was found that it had not been properly heat treated. And so, well, these were a lot of problems with that, but our people kept their determination. Actually, Master Jalpra was there up to a certain stage to help resolve the issues. But as mentioned earlier, it was a heavy water board team with grit and determination that made the technology work. It was imported technology, but it was made to really work. It had not matured, and it was our basically not only Jalpa was there, but it was our effort which made it work. The experience gained and much lower operating pressure, that is about 200 kg per centimeter, helped in setting up and bringing up subsequent plants to full production stage in shorter time. Because the other plants were hooked on to fertilizer plants which were using lower pressure technology. Then, this was the ammonia hydrogen exchange monothermal process. But there's also a version of same exchange but bithermal. So around 1971-72, there was an urgent need to augment heavy water production beyond the projected total capacity of Baroda, Kota, and Tuticorin plant. Those were the three plants some under construction, some were producing. Though heavy water project preferred the familiar French technology at that stage, because we were familiar, an alternate became available, a bithermal ammonia hydrogen exchange process for production of heavy water developed by Ude, a German company. It offered lower energy requirement as well as simple design and equipment more amenable to indigenization. After due scrutiny of the process and offers from Jalpra and Ude, it was decided to go for Ude proposal. The project was sanctioned in 1972. The plant was set up at Talcher in conjunction with FCI's fertilizer plant, which was based on a new coal gasification process. Because oil crisis was there, so India had gone in for two fertilizer plants based on new coal gasification process. Unfortunately, those were not very successful. Then, as the source of deuterium is in these is hydrogen, which forms part of synthesis gas. These need to be integrated with fertilizer plants, hence are parasitic in nature. This I had already pointed out. Their capacities get determined by the quantity and quality of synthesis gas available. Any change in parameters in operation of the fertilizer plant affect performance of connected high water plant. HWB has been meeting these challenges and devising means to minimize the effects. However, in case of Baroda plant, heavy water production had to be stopped after about 2 decades due to the coupled fertilizer plant switching over to another technology with feed to heavy water plant becoming incompatible. In case of Talcher plant, the coupled fertilizer plant hardly worked to its expectation, leading to a similar fate for our Talcher plant. The production at Tuticorin plant had to be stopped in 2007 after about 3 decades of operation of producing on account of coupled fertilizer plant stopping their operations because of their production based on naphtha had become unviable. Well, fortunately, it is now under revival as the coupled fertilizer plant is resuming operations. HWB, I mean, the important point here is that we had to stop the production, but we were very quick to turn these adversities into opportunities by utilizing the resources becoming spare for intensive diversification. This is the reason why we got so much into diversification, and well, finally, it turned out to be a good move. Now, I just have been mentioning various names of the plants. I just want to show you the location. We had the first plant at Nangal, right on top. I think we have this. You could point that out. You could point that. Nangal. Then we have the plant at Kota, which is integrated with that based on our own technology, and the second generation plant at Manguru, based on, again, our own technology, which is scale up of the Kota. The rest of the plants have been are based on ammonia, hydrogen technologies and imported ones. That is one at Baroda, which is a first generation plant, and Talcher also the first generation plant. Then Hazira Thal are the second generation plant. Actually, I'm sorry, Tuticorin is also to be treated down south as a first generation plant for that one. And as I mentioned, the production at Baroda, production of heavy water at Baroda, Tuticorin, and Talcher is not, has been stopped. We are no longer producing heavy water, and we are utilizing the facilities there for all diversified products which I'll be talking about. Tuticorin, of course, is under revival. Now, I'd very briefly show you the picture of this plant, not all, but the first generation plant. This is our first plant at Baroda, based on ammonia hydrogen technology, hooked onto a fertilizer plant. Then we have our first generation, the plant at Kota, based on H2O technology, our own technology, hooked onto, integrated with RAPP for steam and power supply. Then we have, this is our second generation plant, which we have almost done it on our own, is ammonia hydrogen based, the last of the plant. And this is, of course, the plant at Manguru, scale up of the Kota plant, you can say, but with a big difference that it has its own integrated captive power plant, and the steam cycle is fully integrated, so that gives us a great deal of flexibility, better energy consumption, and this, incidentally, I would call it the crown of our whole program, and the largest producer, and a very steady and very good workhorse. Then having already I mentioned, but this is to recap, that this is how we built up our capacity over a period of year. This, of course, the installed capacity. It is not the production. Production is another matter altogether, because there's certain other factors. But these were we started with Nangal, the 14-ton capacity, of course, tuned it down later on. Then we added Baroda in 1977. Soon after that, Tuticorin, 49-ton capacity. Then we added Talcher, and then Kota started producing 1985. Then Thal, another 78-ton. And then we added Hazira and Manguru. This was the zenith of you could say, the setting up of the projects, the new plants. And this was the maximum capacity, that installed capacity, so to say. Soon after that, we started, some of the production at some of the plants we had to suspend at Salter, because the linked up fertilizer plant was never worked properly, and of course subsequently they stopped it altogether. But we found that our operations were no longer viable, and so this was the first one to be taken off the line, and this was the first one, the pioneer in starting the diversification activities. Most of the solvents technology was developed there. And then Baroda too had to be taken off the suspension, because fertilizer changed its technology. And Tuticorin, because again the fertilizer plant for their production became unviable. And now we are going to add in another 2 3 years Tuticorin because they are reviving their thing. But Tuticorin also we have been utilizing for a lot of diversification activities. And then actually there's the time constraint does not permit coverage of very special features of construction and commissioning, which was also a very challenging time and also very interesting also. But because these plans were being set up for the first time in India and there was not enough infrastructure. However, I'd like to share the details of one particular unique feat. I call it a feat because it was really a great feat, if you ask me, related to the transport of main isotope exchange tower of Baroda Plan. This was a 2.5-meter dia, 30-meter long, 330 millimeter thickness, about 13 inches thickness, you can say, a multi-layer high-pressure tower weighing 530 tons, fabricated in France. It was brought as deck cargo on a special ship which anchored in sea off Bhavnagar port, which was the nearest port. At the time of specified high tide, it was lowered on two self-propelled crawlers on a pontoon barge, which was towed to specially prepared jetty at Mujpur. That was the crawlers rolled out on the land for its journey to the project site, 42 kilometers away, through some villages and part of Baroda town. The total weight of the tower and crawlers added up to 700 tons. En route, culverts had to be fortified, diversions made, and care had to be taken to ensure that overhead power lines, underground cables, water and gas lines, railway crossings, etc., were not damaged. It called for a lot of improvisation and ingenuity, what we call in our local languages jugaad, if you permit that word, for completing the journey, which took 19 days. It was almost like a mela route. Sometimes the consignment will get stuck for a day or so. The roadside vendors will come and start selling their goods, almost a big mela. But it was certainly something very unique. And subsequently, also a lot of transportations have been done, but nothing to beat this particular size and this particular length. Now, having set up all these plans, you see, initially we were under tremendous pressure to produce because we were late starters and prospect of becoming bottlenecks for the whole program. So initially we had a mantra of producing at any cost. We were making all effort, not bothering about it. We had to produce, and produce. But once we started producing and we became comfortable with the stock position, our month changed. Now it was produced at the lowest cost. So we started looking at all our systems, all our plans, everything that like examining it afresh. And it was a tremendous effort spread over a very long period of time because a lot of schemes were also devised which needed to be implemented, systems modified. But it was I would say, a tremendous effort yielding a very big result. You can see that from the specific energy consumption. This is the average of all the plant. From 44 gigajoules per kg, it came down to 30. It's a saving of a reduction of about 30%. And we do take a great pride in this exercise. Similarly, being concerned with the environment, we were also looking at all other aspects, and here too, we brought down our specific CO2 emission in heavy water. That means carbon footprint by 45%. Of course, I'm only mentioning about the carbon footprint, but we did a lot of other work, which like making some of the plants zero discharge and conserving all, not only the energy, but the taking care of the environment. So this was another big effort, but this came in only once we started producing and meet the demand. Then, as I mentioned, out of necessity because we had to stop production at some of the plants, heavy water production, we got into diversification. This has been quite a great effort. And what we have done is we took up the materials which are required in the nuclear field for making the country self-reliant. This we have made several conventional and specialized solvents, developed the technology. Part of the technology was developed in VARC. Heavy Water Board has been specializing in transforming any technology that is developed or this initial work is done into transforming it into plant and bringing out the production. So we took up several conventional and specialized solvents for sustaining nuclear fuel cycle, both front and back end. This included organophosphorus-based solvents, amide-based solvents, and also a lot of customized solvents. And actually, we have come to a stage that the other countries are looking to us for the supply of these things, which is again a mantra of Atmanirbharta and exporting. Then we have also worked on recovery of, this is all adjunct to the effort that has come up because of somewhere the heavy water production being stopped. So it becomes a story related to the heavy water. The story is not complete without mentioning these things. So we have also developed a prototype. We have set up a prototype demonstration plant for recovery of uranium from phosphoric acid, which is extensively employed by the fertilizer plants, and plants are on hand for setting up a production plant. And of course, if we can do it for the uranium, there are other rare earths also we can deal with. And then boron tan, which is that also we have taken up. We are producing boron tan, which is needed for fast breeder reactors, also for neutron counters. And I think we have also supplied some of these to France for their research work. Then we already had expertise on producing potassium in Baroda Plan because that is needed for our catalyst. So we started foraying into taking up production of nuclear grade sodium, which is required for fast breeder reactor. So technology has already been developed, and now we are in the process of setting up a 600 metric ton year plant at Baroda. Then another important product that we have made is oxygen 18. This has a lot of application, but the important one is like production of FTG in positron emission tomography. Then it has a great use in research in human metabolic rate, paleoclimatology, and plant physiology as a tracer. Then being in heavy water, we are virtually the sole supplier of the deuterium. Deuterium is a very charismatic isotope. It's actually substitution of hydrogen. With deuterium, alter properties of its compounds, making it a very good thing for applications in non-nuclear side, including life sciences. Then this is actually used as protective, preservative, and pharmaceutical material. It has applications in so many advanced technologies like information technology, electronics, laser technology, optical recording, isotope hydrology, NMR spectroscopy, and so many tracer studies. We are supplying appropriate materials for the above. The examples are like deuterium depleted water. This is, of course, a very fascinating product where it's said to have great advantages and very and the cancer therapy. It's not a for treatment of therapy, but it's for the therapy. And it's actually, as far as we are concerned, it is still work in progress. But uh, elsewhere, it is now becoming quite popular. And in India too, we are working on it, and I foresee that great demand for this will come up. It has also a lot of other good effects on health. Then, of course, it has a application label compounds, which includes deuterated solvents, tracers. Then deuterated medicine, it has a very large uh, application, and the demand for this is growing. Then it is also used as a stabilizing agent for materials like oral polio vaccine, where the cold chain, which is always a problem, can be dispensed with, or for some time you can uh, do without a cold chain. And, similarly, a very big application of deuterium gas, which is being supplied by the our establishment, High Water Board, is for conditioning of optical fibers for reducing signal losses. Now, the around early 1990s, India had become very comfortable with regard to heavy water stock position and decided to foray in export market. South Korea required large quantities of heavy water for their PWR type of power reactors. We responded to their tender, but were virtually thrown out of the race, as they did not believe that India could produce heavy water to meet their requirement vis-a-vis quality and quantity. I might add that we were virtually humiliated because they started showing us some kind of unfriendly press reports which said heavy water runs into heavy weather and things like that. Well, we came back. Then came a second tender. We responded to that also, but backed it with a changed strategy. We decided to throw open our facilities, which so far we were keeping more or less under wrap. We're not very open. We're not showing it to many people. We managed to win an order for supply of 100 tons of heavy water against stiff international competition with proviso that order would be confirmed only after they visit our facilities and are convinced. They did visit our Manguru and Thal plant and were convinced, and they confirmed the order. This not only earned over 22 million US dollars for India, but also built up our reputation as an established supplier of heavy water. India has been exporting heavy water since then to many countries. Important, and the main countries have been France, USA, and South Korea. Well, this is, I would say, Dr. Bhaba's dream was being fulfilled in entirety as far as heavy water is concerned. Now, in conclusion, I just say that India achieved self-reliance in heavy water about 25 years ago and started exporting it too, fulfilling Dr. Bhaba's dream. Today, it is the world leader and stands tall in this field. It is in a position to support countries' projected indigenous PHWR-based nuclear power program till end of current decade with present facilities. Having assimilated and mastered the technology, it can easily meet any additional demand by expanding the Manguru plant with minimum lead time. As related activities, Heavy Water Board made great strides in achieving self-sufficiency in production of many materials as mentioned earlier, required for nuclear and non-nuclear application, including that for life sciences. As of now, the greatest potential lies in the field of non-nuclear applications of heavy water deuterium, heavy water and also deuterium. It will be a game changer, giving rise to considerable demand of heavy water. It has been possible to achieve such a marked success due to a determined, dedicated, and agile heavy water board with can-do spirit. Various collaborative units, especially BARC, where indigenous technology was developed, and supportive Department of Atomic Energy with all its unique features and special dispensations. I just wish to thank Shri Jiten Srivastav, Chairman and Chief Executive Heavy Water Board, and his colleagues, Srimati Manisha Patil and Shri Girish Joshi for their help in preparing of this talk. They have worked very hard to help me prepare this talk. And I thank Professor Rao once again for giving me this opportunity. It's been good to reconnect with the heavy water program. And thank you, the audience, for participating in this webinar. Jai Hind.
Sir, it has been a very fascinating account of how we started the heavy water program at a very small level and we have become a world leader. And your experience came through in your presentation, the kind of hard work, commitment in innovation that you have put in, the entire family of heavy water board. That is really something special to be noted by our young students and faculty who are participating in this program. There are a few questions, I'm sure, on the web, both from the WebEx and from the YouTube. If there are a few questions, I hope you'll be able to take. One question from my side, which of curiosity was such a large program on a long run, which is now more than 60, 70-year old, would have also required a sustained program of human resource development. So how this was handled by Heavy Water Board? Because without very good engineers who are fully familiar with, and then they have to face challenges in the operations and maintenance of very large plants with high levels of safety. How was the concept of human resource development for this handled?
You see, so happens that the Department of Atomic Energy has its own specialty. That means it recruits people on its own and then puts them through the training school. Now, I would mention that this department was a department which was for the future. I, for one, would share a personal experience. I happen to be an engineering graduate from IIT Kharagpur. And I, for one, had more opportunities to work in the industry. And I also appeared for railways and I was selected. But I preferred to join this department because it looked like a department for the future. And when we joined, there was so much to do because everything was new. And that itself was a big challenge. And I think that attracted people, and not only attracted them, and when they started working, there was so much to do, and it was all a virgin field, which was a very big motivational factor for people to be there. Of course, there was some small period where there was a lull, but there was a very good, strong leadership which sustained this thing. Like I want to mention that, for instance, when we were talking of scarcity era, well, there was so much of a difficulty, and then there some people could have easily got frustrated because it was not easy. And everything was scarce. But what was really not scarce was enthusiasm of the people and the challenges that were there that wanted to take, and the encouragement from the leadership. So the manpower has, there will be this tremendous motivation because it was all a new field. And when we look back now, I feel that some of the youngsters who would be joining here perhaps may not be having the same kind of opportunity. But at that time, the opportunities available itself was a thing. And once we got into it, there was no looking back. And as you said that in certain technology like our indigenous technology, we worked from concept to commissioning. So when I was working initially, I was working on the concept. But then I didn't get fed up because the next step was taking it further and further and further. And those were the kind of motivation that was there. And the formal training was there from the training school, but it was virtually the leadership which won the day for us.
Just another curious question. Did, did you have any occasions to interact with Dr. Homi Baba himself? Because most of us here, we have not even seen him.
Yes, yes.
But your own person who have been there.
Well, I would say that no, I was not in the orbit next to him.
Okay.
I was in the orbit next to him, in the second orbit, so to say. So I did not have any personal reaction, but I have seen him and also heard him, but I had no personal interaction with him. But I have seen him when this hall, engineering halls were being made, when Park was coming up. And one Sunday we came for doing some work, and I found Dr. Bhabha lying on the slopes of the engineering hall. The engineering halls were there, and he was lying on the slopes and looking uh, in front, and this mod lab was coming up, and he was a dreamer. It was, even his presence, I mean, I might not have talked to him, but I have been, even if you're in close proximity, you felt inspired. He was, I mean, there was something which you can't quite describe. And, but personally, excepting for hearing in general talks, I had no personal interaction, which was not the case with Dr. Sarabhai.
Yes.
Fortunately, by that time, I had occasion to interact with Dr. Sarabhai, but not with Dr. Bhabha directly.
Okay,
But the aura was there and it was overwhelming. Let me put it this way.
you have, of course, you have written a book also on Dr. Vikram Sarabhai.
Well, yes, that's right. It's a compilation virtually. I mean, because I have had some interaction with him, and somewhere I was had to face him, and he gave me some very pearls of wisdom. I mean, if you want, I can recount a very short one. There was some problem about getting some of our equipment fabricated out of clad materials, and we had rejected, or rather, our consultants had rejected one of the public sector uh, companies. They said they don't have experience, they can't do it, and only such and such other companies can do it. So this was when this went for approval for. Then Dr. Sarabhai said, "No, I don't believe anybody. We should look at it ourselves and decide." So I was deputed to go and assess the. I went there and I came back and I confirmed the finding of our consultants. No, they don't have uh, experience. They can't do it. So this was reported to Dr. Sarabhai. So he said, "Look, I want to hear from the horse's mouth." So I was pulled up and I was put across the table to him, and he asked me. I gave my ideas and all that. Then he asked me, "Young man, have you made heavy water?" I said, "No." So he said, "Well, we can put our faith in you for making heavy water for the first time. Why can't you put your faith in this particular government undertaking to make your equipment and you guide them, hold their hand into it?" So those are the kind of pearls of wisdom. But, but I didn't have the good fortune of interacting with Dr. Bhava.
And one last question from my side is that just like now we are supplying heavy water to many other countries across the globe, do you think similar thing could happen with enriched boron carbide? Because I feel very few countries in the world are really capable of making even enriched boron.
Frankly, I'm not able to respond to that. I don't have enough expertise to in this thing, and perhaps we may take the liberty if chief executive, who's part of the audience, could throw any light on it.
Right in the actually the separation of boron tan and nylon. Otherwise, boron carbide, making the boron carbide is not a big deal actually, in my opinion. In this boron, if somebody will ask, we will be able to supply.
Sir, I think 1.5 hours of the tour. We were taken back to the early days. Yeah, when time has passed so fast, I could see the kind of, it would have been so difficult for you to condense that 70 years of experience into 70 minutes. But I think you have given us a very good taste of what happened, and it's a great pleasure to thank you for joining us and spending so much time with us. I know how seriously you have prepared for this presentation over last more than 15-20 days, and that goes that spirit with which you started the program still that is there in you. We can see that. So we're very grateful to you for joining us on this occasion. And on behalf of HBN, as a small token of our appreciation, I request Professor Grover to hand over a small memento to you.
Let me tell you, Professor.
Yes.
The pleasure has been all mine, and I'm so happy that I have.
Thank you, sir, for a very interesting lecture, and I see many people are commenting on this very good.
And I can tell you that many of the earlier chief executives are online. They have joined the occasion. We are thankful to them. Mr. L. Rao is there. Mr. Mr. Naik is there.
Shri Naik also writing this.
And Bhaskaran is there.
So all of people.
And Mr. Anand also had joined. Mr. Anand, AKAM has joined.
Mr. Mehta is also there.
Mehta also is there. I think all of them would have, I'm sure, enjoyed your
My pleasure.
Your reminiscences and your words. So a great lecture. Thank you very much for joining us.